Assalamu. So you've already seen spin in this course, and today I would like to look at spin from a different perspective and look at some applications of how spin can be useful. So in order to build up the concept of spin, there are different approaches. First of all, spin, the word spin is a misnomer. Misnomer means the word spin does not do justice to the effect. It's not really an object, a sphere such as an electron or a proton that is actually spinning and going around an axis. It's a purely quantum mechanical phenomenon that cannot be visualized by our classical mind. It's purely quantum mechanical. But it works because experiments tell us that spin exists. There's a property that we call spin, which exists and is described by quantum mechanics. We just give it the name spin. It could have been called something else. Just as the electron has a charge, charge is the name that we give to a certain property of the electron. The electron has a mass. Mass is a name we give to a certain property of the electron. We could have called it color. We could have called it hue. We could have called it saturation value. But historically, this property is called the spin. And this spin has certain outcomes in an experiment. And we know that spin exists because experiments tell us that there is a property which is some property which we call spin, and it does exist. Now, how do we build up the concept of spin? First of all is our classical notion of the orbital motion of an electron, which means that if you have a charged particle, such as an electron, and it goes around in a circle, just an electron going around in a circle. Now this is a classical picture. This could be an electron, this could be a ball of charge, it could be anything. There's no quantum mechanics so far. Now when this electron is going around in a circle, this is actually a current. Moving charge is a current. Alright? So when this electron goes around in a circle of radius r, there is a certain angular momentum associated with the electron. If m is the mass of the electron, v is the speed of the electron, then the angular momentum of the electron, which is also a classical quantity. You don't need quantum mechanics to talk about angular momentum. You studied angular momentum in mechanics. This L is simply mvr. There's no rocket science about it. Now there's a massive object moving with a speed v in a radius r. Constant radius, constant speed, it has an angular momentum. Okay? Which means it has some rotational energy as well. Alright, now since this is a charged particle, and we're looking at the orbital motion of electron. Orbital means something going around in space. The electron is orbiting in space. Now, it's fun. Now, since this moving charge is also a current, that's what current is, a charge that moves gives you a current. So if in my mind I have a hypothetical screen, just a plane that cuts the orbit, then a certain amount of charge passing through this screen per unit time. So the electron goes around, it carries some charge, so per unit time, there is a certain amount of charge that is cutting this screen. that is traversing the screen, threading through the screen. Now, if v is the speed and E is the amount of charge, what is the current that this moving charge constitutes? How large is the current going to be? So that's charge per unit time. So we need to know the amount of charge. So the electron passes through the screen once in one revolution. So the amount of charge that passes through the screen in one revolution is E, the amount of charge of the electron, and the time that it takes for one revolution. Now what is the time that this charge takes? It's the distance 2 pi r divided by v. Alright? Distance over speed. Now this is the charge. Now this is purely a mechanical phenomenon here. But since it's a moving charge, associated with this mechanical motion, there is some electric phenomenon that's taking place. Alright? Now if I do a slight manipulation, I take this I, E over 2 pi, and then what I do is R, I have a V here. So what else I would like to do? I would like to put an M here, M. I also need to put an M in the denominator. And then I need to put an R here. If I put an R here, I need to put an R in the denominator as well. I is the electric current. Now this MVR, this bunch of MVR is simply a mechanical constant of motion. It's a mechanical quantity, angular momentum. So I have E over 2 pi r squared m, okay, or L. Now what we're doing here, we're just playing with numbers, putting something in the numerator and putting something in the denominator, and that's what a teacher would like to do. It's uninteresting, but a teacher does this, a teacher like myself does this, because what it shows is that there's a relationship between a mechanical quantity, L, and an electrical quantity, I. And this is some constant. See, all of these are constants here. R is the radius to which this electron is moving. And this is all classical, nothing quantum mechanical about this so far. Now the point is, yes, for electron it is constant. This mass will depend upon the speed, but for a particular speed it's going to be constant. Now what we would like to do, from your school days, if I have a coil like this, and I break the ends of this coil, I put a battery here. There are two terminals of the battery, and I put a battery here. What's going to happen? A current is going to flow through this coil. Now, if you place a compass needle close to this current carrying coil, what's going to happen to the compass needle? Is it going to deflect? It's going to deflect. Because a current produces a magnetic field. Right? A moving charge, which is a current, produces a magnetic field. What's a magnetic field? So if I have a magnet, if I throw this chalk is going to fall down because of a gravitational field. ठीक है? इस तरह सब लोग डिस्टर्ब मुझे कोई फर्क नहीं पड़ेगा लेकिन सब लोग डिस्टर्ब होंगे. ठीक है? So raise your hand. ठीक है? So this chalk is going to fall down because of a gravitational field. There are objects such as magnets which have a magnetic field, and magnetic materials can drop into the magnet because of the magnetic field. Likewise, a moving charge, which is a current, also produces a magnetic field. That's why if you have two coils and current flows through them, these coils will attract one another or repel one another, depending upon the direction in which the currents are flowing. So whenever you have a current, it produces a magnetic field, and it can attract other magnetic objects, magnetic materials into that field. Yes. The Earth has a magnetic field because of different reasons. Previously it was thought that there are magnetic rocks inside the Earth. But so it happens that Earth has three layers: the crust, the mantle, and the core. The core has two layers, the outer core and the inner core. In between the two cores there is a boundary called the Inhomogeneous boundary. Now inside the core, even though it's at high pressure, high temperature, there is a liquid inside the core. And the liquid is circulating. That circulating charged liquid produces a magnetic field. That's the current theory of terrestrial magnetism. So let's move on, otherwise we're not going to finish things. So a moving charge produces a magnetic field. Alright? So this is a similar scenario. An electron is moving, it must produce a magnetic field. Okay? Now how do we measure the amount of magnetism that an object produces? There are strong magnets and then there are weak magnets. But that's the layman term. Strong and weak are just layman terms. So how does a physicist quantify the strength of magnets? A physicist like yourself or an engineer like yourself would like to use a term called the magnetic moment. And is denoted by the symbol mu. Alright? Now a stronger magnet has a large value of magnetic moment. Water molecule, you must have studied in Chem 101 that water is a polar molecule. It acts like a tiny dipole, but that's an electric dipole. Here we're talking about magnetic dipole moments. So suppose I have a magnet, a bar magnet. Conventionally, in our school days, we thought it has a north pole and a south pole. So this picture is not really correct, because you can't have a region which is north pole and a region which is south pole. If you break this magnet, you get a north pole, so-called north pole here. So this is just a cartoonic representation of a magnet. Now, this magnet produces a magnetic field. And if you look at the direction of the magnetic field, the conventional direction of the magnetic field, it's like this. So the magnetic field goes from the north to the south pole, and inside the magnet, it goes from the south to the north pole. Right, and so on. On each point in space, you can draw a vector that is tangent to this line, so the line of force. This tangent to this line shows us the direction of the magnetic field, B, which is denoted as B. Just like a charge has electric field, a magnet has a magnetic field. Now, associated with this magnet, there is a dipole moment, magnetic dipole moment, which has a certain strength, denoted by mu. In this particular case, the mu is a vector that is pointing from the south to the north pole. This is the direction of this magnetic moment vector. It's a vector. must have a direction. Stronger the magnet, bigger will be this vector. So this mu tells us the strength of the magnet. It also tells us the direction of in which this magnet is aligned. If I just rotate this magnet like this, so that this becomes the south pole, this becomes the north pole, then the magnetic dipole moment will be pointing in this direction. Alright? But this is a permanent magnet, yes. Well, you're asking questions that, because it's a relativistic phenomenon, an electric field will act like a magnetic field. A magnetic field will act like an electric field in a relativistic way. Why? There's a complete theory by itself. Now what we would like to do is, I would like to connect this concept of magnetic dipole moment with what we studied over there, and I would like to bring you towards spin. That's the goal. Alright, now this is a permanent magnet, but the same magnetic field can be achieved by a current carrying coil as well. Okay? So if I have a current carrying coil, the one that I've drawn over there with the battery, now I'm not drawing the battery, I just assume that the battery is there. And there is some current flowing through this coil. It's a loop of wire through which current is flowing. And I is the amount of current. Then in your high school physics, your A levels or FSC, you study that a current carrying coil also produces a magnetic field. It behaves like a tiny magnet. So there must be a magnetic dipole moment associated with this current carrying coil as well. And you can easily find the direction of that field. You take your right hand and curl your fingers in the direction of the conventional current, I, and this thumb points in the direction of the magnetic moment as well as the magnetic field. Here the magnetic moment is up, and so is the magnetic field. The general direction of the field is up. Likewise, in this case, a field is going to be produced. The form of that field is going to look like the following. So it's just going to be similar to the bar magnet. And it's going to produce a field that goes upward, bends downwards, and all of these field lines are closed. You cannot have a field line that is cut, which means a field line is a closed loop. A magnetic field line is always a closed loop. Electric field lines can start and stop somewhere. Magnetic field lines can't. Because there is no analog of charge in a magnetic field. There is no magnetic monopole. Anyway, so this current carrying loop also produces a magnetic field B. And it also has a magnetic moment, mu. Now let me draw the direction of that magnetic moment. If this is my current carrying coil, and current is flowing in this direction, I, then my magnetic moment is going to point in this general direction. I take my right hand, curl my fingers in the direction of the current. Magnetic moment is pointing in the direction of the thumb. This is the direction of the magnetic moment, mu. Yes. Magnetic field is a field. It exists in space. It can be produced by currents. It can be produced by magnets, moving charges. The magnetic moment is the property of a material. So this current carrying coil acts like a small magnet, and the strength of that magnet is quantified by the magnetic moment. see the magnetic moment always has this direction, but the magnetic field could point in different directions. So here the magnetic field points like this, here it points like this, here it points downwards actually. So it points upward, here it points downwards. So magnetic field varies from point to point. But this magnetic moment, which has different dimensions than magnetic field, is a property of the amount of charge that is flowing, the velocity of the charge. It depends on this current. Okay? In fact, if I know I and if I know the radius r, I can actually determine what is the magnetic moment. And the relationship which you learn in electricity and magnetism, which is your next course, hopefully, is that if I take the amount of current I and multiply this with the area of this loop, which is pi r squared, I get the magnetic moment. The amount, the strength of the magnetic moment is I multiplied by the area enclosed by the moving charge. Alright? Yes. If I have a loop like this, like an amoeba, this is my current. And I just take this area here. I multiply I with this area A. That would be the magnetic moment. Right? Why? Because I can break up this loop into small loops, this arbitrarily shaped loop into small loops. And it's only at the outer surfaces that the magnetic moments will add up. Here the current is flowing in one direction, here the current is flowing in the other direction. So only the current that is going around this boundary matters. So only the area enclosed by this boundary matters. Alright, so this is my magnetic moment, yes. Yes, then you can't talk about, you have to talk about current densities then. You can always extend this to 3 dimensions, yes. Alright, let's move on. So this is my magnetic moment here. But magnetic moment is a vector. Here, this is a scalar, this is a scalar, the area is a scalar. How do I associate a direction of this magnetic moment? By the right hand rule. So this magnetic moment, if I put a vector here, I need to specify the direction of my thumb, which points when I curl my fingers in the direction of the current. So I have to specify some unit vector in the direction which is determined by the direction of the current. So I need some unit vector. Let's call this A hat. A hat, the unit vector, does not have any magnitude. It has magnitude 1. It just specifies the direction. And this unit vector points in the same direction as the magnetic moment. Anyway, this is my relationship of interest, I times the area enclosed. This is my mu. सबक क्या मिला आपको? सबक ये मिला कि अगर आपके पास एक मूविंग चार्ज है, एक सर्कुलर लूप में जा रहा है, ऑर्बिटल मोशन दिखा रहा है, तो वो मूविंग चार्ज एक मैग्नेट के तौर पे एक्ट करेगा. उस मैग्नेट की एक स्ट्रेंथ है. उस स्ट्रेंथ को मैग्नेटिक डाइपोल मोमेंट कहते हैं. Stronger the magnet, higher will be the value of mu. Larger the current, larger magnetic moment. Larger the area, larger the magnetic moment. Now, if I look at this relationship here, mu, I can visualize in my mind that this moving charge is like a tiny magnet. I can think of it as a tiny magnet whose south pole is here, north pole is here, it's pointing like this. So I can visualize a tiny magnet, which is also called a dipole because it has 2 poles. strength mu, which is associated with the moving current. Now let's come back to this relationship over here. I. This is I. If I would like to find out the magnetic dipole moment of this moving charge, I will simply take this I and multiply it with pi r squared. And that will give me the magnetic dipole moment of this moving charge. Electron, this moving electron. So I take mu equals my I into pi r squared. What is I? I is given here. I multiply this with pi r squared. I'm left with E over 2m L. Is alright. Now, a moving charge, like an electron, has an orbital angular momentum. Orbital angular momentum. And associated with this orbital angular momentum, there is a magnetic dipole or a magnetic moment. And let me write down the word dipole. Okay? Agreed? Mechanical motion of a charged particle is making that charged particle act like a magnet. And magnet can be deflected by magnetic fields. This is a Stern-Gerlach experiment. Anyway, the only thing that needs to be done to complete this picture is this a vector? Is angular momentum a vector? आप बताओ मुझे angular momentum vector है कि scalar है? Vector है? हाँ, बिल्कुल vector है. So angular momentum is a vector. So I need to put an L here. Vector sign, right? This is also a vector. But the only problem is that since we're talking about a negatively charged particle and our magnetic moments are defined with respect to conventional charge, positive charge, I put a minus sign here. That just completes the picture. It completes the story. So I have an electron. Suppose the electron, which is negatively charged, is going around like this. This is the direction of speed or the motion of the electron, which means that the current is actually moving in this direction. The direction of the conventional current is opposite to the electronic charge. Now, since the mass is moving in a counterclockwise fashion, the orbital angular momentum is pointing up. But since the current is moving in a clockwise fashion, the magnetic dipole moment is pointing down. And both of them are anti-parallel. They are in the opposite direction. So this is the story of the orbital motion of an electron. The orbital angular momentum, classically, could be electron, could be any negatively or positively charged particle, is related to magnetism, is related to the magnetic moment. And this is a constant which depends upon the properties of that particle, charge and mass ratio of the particle. So this is orbital motion of electron. Yes. देखो angular momentum कैसे find करते हैं direction? You take the mass, the direction of the velocity, and your thumb points in the direction of the angular momentum. Up. Magnetic moment, however, is downward because the direction of the current is opposite, because it's a negatively charged particle. If this were a proton, then both of them would be pointing in the opposite direction. Yes. Because it's a negatively, the conventional current is generally taken to be due to a positive charge. Okay? Now, what does this have to do with spin? The key idea is whenever you have angular momentum, it gives rise to magnetism. It gives rise to a magnetic moment. Now there was an experiment that was performed in 1932, and you studied the experiment, the Stern-Gerlach experiment. पढ़ा है ना Stern-Gerlach? आपकी नोट्स में था ना ये? Stern-Gerlach experiment में क्या होता है? कौन सा एंगुलर मोमेंटम? Alright, so this is orbital angular momentum. Let me clarify this concept. This is orbital angular momentum. So far the picture is classical, but now quantum mechanics steps in. Quantum mechanics tells us that if we have an electron, say, inside an atom, its angular momentum is quantized. It can only take up specific values. Agreed? If I measure L, now L is a vector, so I can measure three components: X component, Y component, Z component. If I measure one of the components, say the Z component of L, I also gave you a lecture before midterm, didn't I? On measurement stuff. It's about waves, but then collapse of waves, and you measure something, you get electron somewhere. So if instead of measuring the position of an electron, I measure its angular momentum. So now I'm choosing to measure the angular momentum of an electron. But angular momentum is a vector, it has three projections. I can measure either the X component, the Y component, or the Z component. I choose to measure the Z component. That's my choice. Which means I need to know what is the Z axis. So I do an experiment in which I define a Z axis. I make the experiment such that I know what the Z axis is, which means an axis, I choose an axis which is different from anything else. That's how I break the symmetry of space. So if I put a magnet like this, so I have a coil of wire, current is flowing through this coil. So if I have this arrangement, and this is space here, this is iron, so current is flowing through this coil, this will act like a north pole and it's going to produce a magnetic field pointing from this direction to this direction. This is the direction of the magnetic field produced by this current coil. So I have an electromagnet. I pass current through the coil of the electromagnet, it's going to produce a magnetic field. Now this magnetic field is pointing in the upward direction. So I have chosen an axis. So somehow I have to choose an axis. I have to choose a Z. If I say I'm measuring the Z component, someone might ask, what is the Z axis? What is your Z direction? But I have to break the symmetry of space. I have to establish a Z axis. Which means I have to make an axis which is unique. Which means I have to make an axis that is different from anything else. That's how I say this is a Z axis, right? Otherwise, all axes are the same. Which is the Z axis? There's none. So I have to break the symmetry of the problem. I have to choose a Z axis. Mobile phone down, please. So I choose a Z axis and I would like, now an electron, say here. Somehow I'm trapping the electron here in this region and I do an experiment in which I would like to measure the Z component of the orbital angular momentum. Now, experiments tell me that this Z component is quantized. It cannot have an arbitrary value. It has to be quantized. There are only precise values that this component can take. And those values, they are given by L, which is some number, L plus 1 under root h bar. I only get these precise values of orbital angular momentum. Now if I look at this equation over here, yes, L could be 0, 1, 2, 3, up to a certain maximum, but this is the whole number. Depends upon the orbital, but generally a whole number. Now, if I measure the z component of the orbital angular momentum, this is a vector equation. A vector here and a vector here. If I measure one component of L, if I measure the z component, then I can also write down the z component of mu. This is just a constant here. Because these are two vectors pointing anti-parallel and connected by a certain constant of proportionality. That's it. So my mu z is going to be equal to minus E over 2m Lz. Agreed? Simple common sense. Now this is quantized. This can only take up specific values. For example, this could be, if L is 0, this could be 0. If L is 1, this could be under root 2h. If L is 2, this could be under root 6h. If L is 3, this could be under root 12h. And there's nothing in between. It's like a ladder, an unequally spaced ladder. So this is quantized. This is quantized. This must be quantized as well. The magnetic moment now is quantized. Now, how do I know if I have, I need, now let's talk about an experiment that can actually show us this quantization. Okay? An experiment that reveals this quantization. Yes. अब क्वांटम मैकेनिक्स आ गई, क्योंकि यहां से क्वांटम मैकेनिक्स नहीं चलाने वाली, वो कूद पड़ी क्वांटम मैकेनिक्स, यहां से आगे क्वांटम मैकेनिक्स बताता है this is quantized, and you get this quantization by solving the Schrodinger equation. Now this is our relationship, and in order to make sense of this, in order to have you believe this, one has to perform an experiment or show the outcomes of an experiment someone else has performed about 80 to 90 years ago. And that's what Stern and Gerlach did in 1932. The basic idea is as follows. I'm going to move towards spin, so I'm going to end this lecture with convincing you that there is something called spin. What is spin? That's where I would like to end my lecture. Two sentences can summarize what we've learned so far in just two sentences. What are the key ideas that we've learned? First idea, just two sentences. Pehla sentence. A moving charge is a magnetic dipole moment. A moving charge is a magnetic dipole. Right. Second, yes. Right. So whenever we have angular momentum associated with it, there's a magnetic moment. The third key idea is that if the angular momentum is quantized, the magnetic moment is quantized. The only thing is that we talked about orbital motion, orbital angular momentum so far. Now, how do we test that this relationship actually exists? Suppose I produce a magnetic field which is not uniform but an inhomogeneous field. An inhomogeneous field means there is a field gradient. The field is stronger somewhere and it's weaker elsewhere. How do I do that? Suppose I have the same kind of electromagnet coils, but these are pole pieces. These objects, these iron pieces, these are called poles or pole pieces. I make these pole pieces in a particular shape. Like this. So still there is a coil that is wound around these pole pieces. And still there is a current, but now the direction of the magnetic field is, because the shape of these pole pieces, it's going to go like this. Right? So this is vacuum here. In between the pole pieces, the magnetic field lines are fanned out. They're further apart in this concave part of the pole pieces, and in this convex part, they're bunched together. Whenever field lines are closer together, the flux is tight here, and flux is sparse here. So the field line is further apart. The field, magnetic field is stronger here, and it's weaker here. Okay? So this is how you can produce inhomogeneous magnetic fields. Weak somewhere and strong elsewhere. Stronger here. Now let me give you a statement, and for the brave-hearted I'll give you a mathematical reason, but whenever you have a magnetic moment, mu, now I'm drawing the magnetic moment just by an arrow, which is good. I can do that because the magnetic moment is nothing but a vector. So I'm drawing the magnetic moment by a vector. Now if I place this magnetic moment inside the magnetic field, which is uniform, a uniform magnetic field. How do I know that this is uniform? Because the field lines are spaced equally apart. It's a uniform field, a uniform magnetic field, or a homogeneous magnetic field. If that is the case, no force acts on this magnetic moment. There is no force acting on the moment, which means it cannot do linear acceleration. No force. Okay? So if I have electrons coming into this region, this is my electron with a certain L, certain angular momentum L, which means a certain magnetic moment mu, and now I have a z-axis because I've defined the direction of the magnetic field. So a certain Lz and a certain mu z, then this electron will not experience any force. So it's going to move straight through, unscathed. It's just going to pass in straight line. Because it has a certain velocity, it has a certain momentum, it's just going to pass in a straight line in a linear fashion. It's not going to be deflected, left, right, up or down. Eh? क्योंकि force नहीं act होगी. क्योंकि ये मैंने बताया कि if a magnetic moment is in a uniform field, there is no force acting on it. But there is a mathematical reason मैं अभी बाद में बताऊंगा. If a magnetic moment is inside a uniform field, no force acts. Now you have to take my word, otherwise, how do I know that there is no force? Because you don't need to understand this, but if you do, that's alright. If I have a magnetic moment, mu, and I place it inside a magnetic field, B, then there's an energy associated with this configuration. And that is given by the dot product of mu and B with a negative sign. So this is the energy of a dipole placed inside a magnetic field. And if you would like, if I know the potential energy, this is the magnetic potential energy. From potential energy, can you determine forces? Can you, if I give you the energy, can you find out the direction of the force? And the magnitude? Is there a relationship between energy and force? What is that? Yeah, what's differential form? F dot ds is energy. So I take the derivative of this with respect to space. I take the integral of force, I get energy. And if I take the derivative of energy, I should get force. So if I would like to compute the force F, that's equal to minus the gradient. You should calculus 2. The gradient of the energy. You study calculus 2. No? Or it's minus the derivative of the energy in the x direction minus the derivative of the energy in the y direction minus the derivative of the energy in the z direction. ये वाला ग्रेडियंट है, इसलिए मैं आपको बताना नहीं चाह रहा था क्योंकि ये एक और तरफ बात है। ये वाला ये इलेक्ट्रोमैग्नेटिज्म से है, ठीक है। अभी इसलिए you should take my word. If you, does anyone understand this? No one? ये फॉर्मूला कहां से आया है? If I have a magnetic field and a magnetic moment pointing in the direction of the magnetic field, if I take a compass needle, it likes to point in the direction of the magnetic field. You agree? The compass needle, it points in the direction of the Earth's field. So the lower energy configuration is the one in which the magnetic moment and the external field, they are aligned together. And the highest energy is the one in which the field is in one direction and the moment is in the opposite direction. So that's why you have this negative sign. First of all, energy has to be scalar, but mu is a vector. So I take the dot product with another vector. The other vector I am dealing with is magnetic field, because I am placing the magnetic moment inside the magnetic field. So I take the dot product of the magnetic moment with the magnetic field to get a scalar. I get a scalar. I get this negative sign because I would like the mu and the b to point in the same direction. That gives me a negative energy, which is lower. And if these are in the opposite direction, I get a positive number, which is higher in energy. That's where I get this formula from. This is the energy. Now, the energy is minus mu b cosine of theta, where theta is the angle between mu and b. Alright, now from the energy I can find out the force. Quick example. Gravitational field. Easiest example. What's the energy, the gravitational potential energy of an object inside gravitational field? Of mass n, height y, or height z, what's the energy? आप बताओ? आप हाँ, पीली कमीज में ठीक। एक ऑब्जेक्ट है, मास m है, हाइट y पे है. What's its potential energy? mgz, right? Now I would like to find out the direction of the gravitational force. I take this energy and find its derivative with respect to x. What's the derivative with respect to x? 0. What's the derivative with respect to y? 0. What's the derivative with respect to z? mg. I put a minus sign with it and take the z direction. So the force is pointing in the negative z direction. That's what it is. So now I have tried to make sense, quick sense of this formula here. Now if my field does not change with space, if my field does not change with space, then this term is always 0 because there is no derivative with respect to space. So if I have a uniform magnetic field, there is no force acting on the dipole. समझ आई बात की? Well, if I have energy, I can take the derivative with respect to space, x, y, z, and that will give me the total force. Now, if something is not changing with respect to space, it's the same everywhere, then the derivative with respect to x is 0, derivative with respect to y is 0, with respect to z is 0. Everything is uniform, so there is no force acting on the dipole. So if my magnetic field is not changing in space, there is no force acting on the dipole. Alright? Now, hence, if I have a uniform magnetic field and a magnetic moment inside that uniform magnetic field, it does not experience a force. Okay? However, if I make the field non-uniform, inhomogeneous, then I have a derivative with respect to z, say this is my z-axis, which means there is a force point acting on the dipole with respect in the z direction. Okay? Agreed? So now if I have an electron with a certain angular momentum L, with a z component Lz, I'm sorry, मैं गलती कर गया. Lz is not, this is some mlh, some constant ml, whereas L, the magnitude of the total angular momentum is L plus 1 h bar. Sorry. Now if I have an electron of angular momentum z component Lz entering this field, non-uniform field, it can experience a force. Okay? Now what happens is, my Lz is quantized. This thing. So my mu z is minus E over 2m. Lz is quantized. It can take up only specific values. ml into h bar. So I'll put h bar here and ml here. Okay? Agreed? Okay, now last 5-10 minutes is a moment of truth, because we're going to get something really interesting here. यहाँ तक कुछ चीज समझ में आई तो? Is this clear so far? Now, if I would like to find out the force, this electron with a certain angular momentum enters this region here. I would like to find out the force. I know that this is the magnetic moment. What is the, let's first find out the energy of the dipole when it enters this non-uniform field. The energy is given by this, minus mu dot B. Now, what direction is the magnetic field pointing in? It's pointing in the upward direction. Alright, pointing in the upward direction, but it's weaker at the bottom and stronger at the top, but still pointing in the upward direction. Okay? still pointing in the upward direction. So the magnetic field is B and it only has a Z component. So my energy is minus mu dotted with B, but since this is a dot product and B only has a Z component. See, if I look at this dot product, it's minus mu x bx mu y by plus mu z dz. This is how I expand a dot product, right? नहीं तो दूसरा तरीका लिखेंगे mu b cosine theta. If you write this in terms of projections, this is how you write this dot product. Now what is bx? 0, because the field is pointing in the z direction, upward. This term is 0. What is this term? 0. Only this term survives. This term is non-zero. So I get minus mu z dz. So I have the energy. Now I would like to find out the force acting on this electron, which is a tiny dipole. Now I take the derivative of this energy. My force is the derivative of that energy. I have to take the derivative with respect to x of the energy. What is my energy? It's minus mu z bz. This will give me the x component of the force minus the derivative with respect to the y direction, minus mu z bz y. I'm just putting in the energy here. Minus, now this is a force, it's a vector. Minus the derivative with respect to z of minus mu z bz acting in the z direction. Now does bz change with x? No, this term is 0. Does bz change with y? No. Remember that b has a component along the z and it can change along x, y or z. But bz doesn't change along x or y. bz, however, does change along z because the field is weaker at the bottom and stronger at the top. So there is a derivative of the field. There is a gradient in the field. So if I look at this expression, this minus sign comes out plus this mu z is just a constant, right? It's just this constant over here. And it depends upon ml, but ml is just a number. Right? So instead of mu z, I can put in this value here. So mu z is E. Mu z is negative, right? So ये दोनों माइनस मिलके पॉजिटिव और एक नेगेटिव वहां से आ गया माइनस E H bar over 2m, which is the mass of the electron, into ml. This is the force acting along the z direction, unit vector z. अब देखो एक इलेक्ट्रॉन आ रहा है, ठीक है? फर्ज करो यहां से इनहोमोजेनस फील्ड शुरू हुई है, इलेक्ट्रॉन आ रहा है, जाहिर है जहां फील्ड जीरो है उसमें फोर्स नहीं एक्ट होगी, आ रहा है, अचानक it enters the inhomogeneous region. Now a force acts along the z direction. ऊपर जा सकता है, नीचे जा सकता है, कहीं भी जा सकता है ना, ठीक है? अब आप क्या करें कि you place, sorry, BG, sorry मैं भूल गया, sorry भूल गया, ठीक है? BG भी कांस्टेंट है, यानी B, ओहो, sorry, derivative लेना ना, so it's the derivative of bz with respect to z, which I can write this as db z over dz. This is how much the field changes with distance, which is a constant in the direction of z. This is the gradient of the field. How much does the field change with z? So, if this is my z-axis, this is the bottom pole, this is the top pole. If I plot bz with respect to z, then bz has some value at the bottom pole and it constantly goes up at the top pole. So the slope of this line is this thing. This is constant. The field is weaker here, but it gradually grows in a uniform fashion. A non-uniform field whose strength is constantly increasing in a positive slope. So the slope of this line is this quantity here, right? And it's a constant because it's, you have to design your magnet in such a way that it remains constant. That can be done. This is an engineering problem. So now you have an electron coming in. All of this is a constant. This number, however, determines the force. So now what you would like to do, if I would like to find out what this number is, this is given you by the design of the magnet. These are fundamental constants. The charge to mass ratio and Planck constant divided by 2 pi. Now if I put a screen over here, I put a screen. And these electrons are coming in. If they experience an upward or downward force, then they can move. If they experience an upward force, they will move upwards. If they experience a downward force, they will move downwards. The different possibilities. Now this screen is designed in such a fashion that whenever an electron falls onto this screen, it gives you a glow. It just puts a spot over there, like an X-ray film. So by looking at what pattern you see on this screen, you can determine what is ML. Right? If ML is just one number, say 1, just one number, 1, then the force is of one kind. So it will give you a spot over here, say. If ML is -1, it will give you a spot over here. In one case the force is positive and in the other case the force is negative. And actually by looking at the length of this non-uniform region and the strength of the gradient, you can actually determine this angle theta, and from that you can determine what is the amount of force. This is a simple mechanics problem. And if you knew the initial velocity of these electrons and you knew how large is this region, the speed of the electron, so the time of flight of the electron, it remains in here, you can see how much is it going to be deflected. The mechanics problem. You should be able to do it as a homework problem. Anyway, by looking at the spots on this screen, you can find out what ML is. If ML is +1, you get a number here. -1, you get a number here. Because in one case the force is positive and in the other it's negative. If ML is just continuous, it's not quantized, you'll get a smear of points. Right? You'll get a smudge of points. So by looking at the spots on the screen, you can tell what ML is, and it turns out that if L equals 0, we can determine what if L equals 0, which is the angular momentum is 0, small l is 0, ML is also 0, you should get 0 force. Because when ML is 0, you should not see the electrons being deflected anywhere. But when this experiment was actually performed on silver atoms, which in the ground state have L equals 0, and one looked at the screen, Stern and Gerlach looked at the screen, they found two distinct spots, which means that there is some quantum number ms. L is 0, so ml is 0, no doubt about this. But there's some other quantum number, let's call it ms, which takes two values, plus something and minus something. And when one looked at the distance that these spots were on the screen, and one knew the distances between the magnet and the screen, and the length of the magnets, and the initial velocity of the electrons, one can actually determine what ms is going to be. And it turned out that these two spots corresponded to ms being 1/2 and this ms being minus 1/2. Exactly. Which means that even though these electrons had an orbital angular momentum L of 0, there is some other angular momentum over and above the orbital angular momentum, which is called the spin. Okay, let me finish. I'm in the middle. So there is some angular momentum called S. Another angular momentum, which has dimensions of angular momentum, just like L. L has dimensions of angular momentum. जो भी इसके units हैं, kilogram, meter per second, MDR, kilogram meter square per second. So this S is also an angular momentum. Kilogram meter square per second are its units. And if I look at the Z component of this angular momentum, then it's quantized according to ms h bar. And exactly the same formula holds true. Where is my formula? This thing here. The only thing is that I have to replace this L with an S. E over 2m. I can put the minus sign, and then there could be some other constant G, 1, 2, 3, which is well known from experiments. And this is my magnetic moment mu due to the spin. So there is an angular momentum, orbital angular momentum, and it gives rise to an orbital contribution to the magnetic moment. And there is a spin angular momentum, which gives a contribution to the magnetic moment as well. And the total magnetic moment mu is going to be a vector sum of the magnetic moment due to the angular momentum and due to the spin. This is orbital motion and this is spin, intrinsic, nothing to do with the motion of an electron in space. So if I had another lecture on spin, we could take this idea further, but this was the first idea that an electron, even though it has zero orbital motion, it's in the ground state of hydrogen atom, for example, which is in the s orbital, does not have orbital angular momentum, but still it has spin, and there are two possibilities for spin: pointing up in the direction of the field, pointing down in the direction against the direction of the field. Alright, thanks a lot.